All right, so this session is being recorded. We'll be writing some more code, and previously we left at understanding, in fact, talking about insertion sort, which is one of the three sort mechanisms that we have seen so far, which is bubble sort, selection sort, and insertion sort. Um, they kind of have similar performance, and it's not very optimal. They all are n square, which means if your number of data points increase, the time your algorithm is going to take to sort things is going to increase as a factor of square, which quickly becomes a big number. So if your data size is 10 elements, then 10 square is 100. But if it is 1,000 elements, then right away it becomes 1,000 times 1,000 complex. So why are we looking at these sorting mechanisms in so much of detail is because it's very central to data handling. Knowingly, unknowingly, we often tend to sort data. Every time we do a search on internet, um, we generally see the results in uh, some order, right? Recommended order or like most popular order or something. Even while shopping for goods and merchandises online, we like to see things maybe show stuff that have highest discounts first, or sort the products from based on size, or maybe based on price. So we use sorting so much that we don't realize how much we use it. It just becomes part of our lifestyle. That's why sorting has been kind of central to computer science studies, wherein attempt is being made to get better at sorting. So far, the most widely used algorithm of the 20th century is actually a sorting algorithm, and nothing else but a simple sorting algorithm, which actually we'll be looking at. So we'll be in fact looking at um, uh, you know the best uh, algorithm of the 20th century, and we'll see how easy it is, and um, how simple ideas reduce complexity of a problem. Um, so, without spending much time on building the background of it, let's quickly jump to that. And today's session we'll start with looking at a sorting algorithm called merge sort, and we'll see how intuitively simple it is. And then once you understand it fully, we'll see coding it up is also comparatively simple process. So I'm going to take my earphones and mic because I'm going to take it out. I'll try to speak up as loud as I can. Let me know if you all follow or not, and I'll adjust accordingly. Feel free to unmute and ask questions. Questions are really good ways to learn more. Uh, is better The best way to learn is through inquiry. That is through asking questions. All right. So I hope the whiteboard is visible. Let me make sure. Okay.
For some reason, your camera's like really blurry for me. It's hard to see.
Same for me too.
It's like blurrier than usual.
Same. Yeah, it's a little blurry.
Maybe it's your internet. I don't know.
Yeah, maybe it's my internet. Okay, let's give it a moment. Maybe it'll just adjust by itself. If not, maybe I'll quickly drop off the call and reset my router. Meanwhile, I'll just clean the whiteboard. Is it any better or still blurry?
Still blurry.
It's still blurry.
Still blurry.
Let me drop off the call real quick, and I'll join back in like 2 minutes. Sorry, guys.
You're muted.
Oh my bad. Is it any better than last time? I just reset my router.
It's still a bit blurry, but I think it looks better.
Thank you. And I try to write big, just in case if it gets blurrier. It's kind of easy to still see it. And I'll recommend you guys kind of write it down on a piece of paper and then follow along with it. What I write here on the whiteboard, that way you can refer to that if things are not clear here. So we'll start with, uh, let me generate a um, random array again. I should have, um, all right, so let's have an array of how many elements? 1, 2, 3, 4, 5, 6. All right, 6 is fine, I guess. The numbers are, let's say, 14, 37, 92, 0, and this is 72, and this is 5, right? So let's assume this is our array, and now we're going to look at how a simple idea makes it so easy to sort it. So far, what we have done is we have looked at three methods, and in all three methods, each element is compared against each one in like a repeated pattern. That's why we get a n square complexity. And we'll see how this idea is very genius. Now, to understand this idea, let's break down the problem. Our first element is 14, right? And we have an array of how many elements? 6 elements, 0, 1, 2, 3, 4, 5. So we have an array of 6 elements. Now let's assume that our array was only one element, which is just one, and it had 14. How do we sort this one element array? Well, it is one element array. There's nothing to sort in it. It's already sorted. Now, let's say if we had an array of two elements, 14 and 37. Now, how do we sort this? Well, we'll compare these two, right? And one way is we'll make a temporary array of two elements, and we'll compare which one among them. So we are talking about the natural order, which is ascending order. Smallest element is at the 0th index, while the largest element goes to the nth index. So if we have an array of two elements, we create a temporary array of two elements, and then we compare these two. Which among the two is smaller? 14 is smaller, so that we write that in the temporary. We'll just call it the star array. We write 14 first, and then we write 37 after that. Simple enough, right? Now, let's expand this to have three element array. 14, 37, and just for a variation, we'll put 0. Right? And now we need to sort this. How would we do that? Well, we know that three element can be broken down into a two element array and a one element array, right? We can break it that way, or we can break this into multiple combination. And we know, so let's say if you break it down into this fashion, wherein we have the first two elements as, we consider that as like a two element array, and the last element as a one element array. Or maybe, for simplicity and relevance, let's break it down into a different format. So we have three element array. We'll break it down into two arrays, one single element array, and the other is two element array. Now we saw that a single element array is easy to sort. There's nothing really to sort in it, so it will remain as is. And here we saw that we can sort two element array by creating a temporary two element array and then copy pasting things here. So how do we sort the second part of the right hand side of the array? Is we'll create a temporary array of two elements. We'll compare 0 and 37. Which one is smaller? So 0 is smaller. 0 comes here, 37 comes there. And now that's 1. And our 14 is as is, because it's just one element array. There's nothing to sort. But this is not the final output. The final output should have three elements in it. So we create a three element array, like a temporary array. And then what we do is, we know that the first element is a single element array. So we divide this whole array into two halves, right? Two parts. The left part is a single element array, right part is two element array. Now we create a three element array, which is our final output. And what we do is, we compare the first element of right side with the first element of the left side and see which one is smaller. Okay, so we compare 0 with 14. So 0 is smaller, so we copy that over. And as we have copied an element from the right side, we increment the index to the next element. Now we have our index here, our left-hand index is still at 14. Now we compare 37 and 14. Which one is smaller? 14 is smaller, so we put it here. And as we have copied the element from left side, we increment the pointer, but now the moment we increment the pointer, it is bigger than the size of the right array. So it means there are no more elements here, and then the only element left is everything which is on the right side, which is 37 here in this case. Right? Very simple. So what we are doing here is we are breaking a bigger problem into smaller problems, and then we know how to solve a small problem. So we solve these small problems, and then we combine the solution into the final result. And that's very genius. Is sometimes the problem is too big to solve in one go, so we break down into smaller pieces. So we break down this whole array into these individual items, and then we start combining them. So one element array combines to become two element array, and then we compare two such arrays to make it a four element array, and so on and so forth. And at the end, we'll have a sorted array. So just to make sure that we understand this concept well, let me change these two elements in our original array. The element at index 2 is 0, whereas index 3 is 90, 92 is. We just make it 90, doesn't matter. Now, we sorted the first three elements. Let's assume our array was 4 element wide. Okay? So this is our original array. It has 4 elements in it: 14, 37, 0, and 19. Now we need to sort this in ascending order. So how do we do that? Is so how do we do this? Is we break the whole array into two halves. Right? We'll call this the left half, or sorry, the right half, and this is the left half. Right? Now we look at the left part. So left part is 14 and 37. The right part is 0 and 19. Correct? Now we take the left part and we further divide it into two halves. So now we are left with 14, which is single element array, and 37 is a single element array. So we go and sort them first. So sorting 14 is nothing, like there's a single element array. You don't really sort it. Now we come back to this level, and now we originally started with 2 elements. We broke them into 2 individuals, and we sorted each individual. And now we know that both ends are sorted. We combine them together, do a temporary array. So we make a temporary array, and we combine them. Which one is smaller? 14 is smaller than 37. 14 comes first, then we copy 37. Okay. Now we know that our left side is sorted. Now we'll go and tackle the right problem. The right side we have our 2 element array, which is 0 and 90. We break that into 2 halves, which gives us 0, which gives us 90 as 2 single element arrays. So we go and sort them, and we come back to this level, and now we know that everything to the left is sorted, everything to the right is sorted. So let's merge them now. We create a temporary array, and we try to merge them. Which one is, we compare each element, and 0 is smaller than 90. So 0 comes first, 90 follows. So at this point, our left hand is sorted, right hand is sorted. So we come back to this level, and now we want to merge the 2 sorted results. And we do that by creating a temporary 4 element array, a temporary array. And we start, so we have one pointer here, we have one, so let's say this is our I, this is our J. And we compare I with J, and whichever is smaller, we copy that element in the temporary array. So is 14 smaller than 0? No, 0 is smaller. So we copy 0 and then we increment the j pointer or j index. We don't do anything with I because we have not copied anything from the left half yet. Now we compare 90 with 14. Is 14 smaller than 90? Yes, 14 is smaller than 90. So we copy 14 in the temporary array and we move the I index to the next element. Okay. Now we compare, is 37 smaller than 90? Yes, 37 is smaller than 90. So we copy 37 next and we increment I. But then the moment we increment I, value of I is bigger than the array size, which means it means that we have looked at every element on our left. So the only thing remaining is all the elements on the right, j and beyond. So in this case, there's only one, so we copy that as is. If there were more, we would have just copied them over. So essentially, we see is in our temporary array, our data is sorted now, right? So what we did is we started with the original array, we broke it into halves, and then we sorted each half first, combined the results, and finally we get a combined result, right? Any questions? No questions, right? So let's, well, we have kind of worked on the example here, but let's look at the whole array and kind of quickly break it down. But two things to note here is two operations that we do here is first is we when we break down our array, we finally reach two single elements at the end. So we are sorting those single elements, and then after the sort is done, we are combining the results, right? So once we sort all of them, then we combine them, which means we come back here. Now the combined result is sorted. So we combine that sorted result. And then we'll see that how we are first solving, first we are sorting everything to the left, then we are sorting everything to the right. So at any point in time when we are sorting only one half of the partition. So we are partitioning the array and we are sorting only one half of it at a time. Right? So let's quickly run this example. And then we'll write a code for this. All right. So we'll see. So where do we partition this original array? We take the length of array. It's 6 in this case. So we do a half. We say, where's half of this? So 6 divided by 2 is 3. So that is essentially 0, 1, 2. So we say this is our half. So we divide the array right here. So we get 2 halves. In one half, we have 14, 37, 0. And the other half, we have 90, 72, and 5. Right? So now what we do is, we'll first sort the left side. So the first step in sorting is to break the array further down. So now we have 3 elements. Now what is half of 3? 3 divided by 2 is 1.5. So it's an integer. So it means 1, which means we break the array like such. So we get sub-arrays. 14 is single element array. And we get 37 and 0 as 2 element array. Right? So now we solve, we sort the left first. Now in the left hand side, we see there's only one element, there's nothing to sort. So it's already sorted. So now we sort the right side. Now there's 2 elements in it. So the first thing before we sort is we break it into halves. So 2 divided by 1 is 1. So essentially we break the array here. So now we are left with 37 as single element and a 0 as single element, right? And once we have broken down the array, next thing we do is we we sort the left. In this case, it's 37, it's already sorted. We sort the right, 0 is already sorted, it's single element. And after sorting, we combine them together. So we create a temporary array, and we call it temporary array, and we combine the result. So which one is smaller? We combine this. We compare index j and I. Where does j start at? It starts at wherever the half is plus 1 is jth index, and I starts at a 0, right? So we compare the 0th index with whatever the half was plus 1 index, which is j. Which one is smaller? J is smaller. So we copy whatever is at j into the first index. Let's call it k. Our k was 0, so we copied something at 0th index. So now we increment k. So our k is at 1, and we increment j, but then now j has become more than size of array. So and there's nothing left on the right side. We come back to I, and we say, well, there's nothing left to compare 37 with, so it means 37 is the only element that we copy that over. So now we had our left side sorted, which was 14, and now we have our right side sorted, right? So what we do next is we combine them. So we create a temporary array of 3 elements. We say k is 0, our I is 0, and j index is, so what was the half here? It was 3 elements, half was 1. So our j starts at half plus 1 index. So in this case, as it is 0 base, so j starts at 1 index, right? So we compare, is 0 greater than 14? No, it is not. So 0 is copied over here. K increments to 1, which means next whatever element is copied at index k. J increments because we got something from the right side, so we increment that j index. Now j is 2. We compare 14 and 37. Is 14 smaller than 37? Yes, 14 is smaller. So we copy the 14 here, and now we increment our k, saying the program that whatever next thing you copy at index 3. Now we copied something from left side, so we increment I. Now I becomes 1, but that's greater than the size of it. So it means we have copied everything in the left. The only thing remaining on the right will be we just copy it over as is because this is already sorted. The only thing remaining here is 37. So now we have our left-hand side of array sorted. So we come back to this. So once we have this, we come back to that level. And now at that level, we sorted the left side. So now we're going to sort the right side of the array. And we follow the same principle, is to sort this, first we break it into 2 parts. 3 divided by 2 is 1.5. So our partition is going to be right here. So we are left with a single element array and a 2 element array, right? 72 and 5. The rule that we have in our mind is first we sort the left side. So we try to sort 90. Well, 90 is already sorted because it's single element. Now we try to sort the right side, and now it has 2 elements in it. So first thing we do is we partition it into 2 halves, right? So we break it down into individual elements, and now we sort the right side. 72 is already sorted, and then 5 is also already sorted. So now we have sorted both sides. The next step is to combine the result. So when we combine it, we make a temporary table, or we make a temporary array, and we compare our I is 0, j is 1, our k is 0. We compare ith index with value at jth index. Is 5 less than 72? 5 is less than 72, so we copy that over and we increment j. So now j is 2, which is more than the length of array. So there's nothing left on the right side to copy. We come back to the left side, and as there's nothing else to compare against, we copy everything over as is. So now there it is. And then this was 90. So now we have, so we were here, we sorted the left side, We went and sorted the right side. So now we have the sorted result. Next thing is to combine these two. So combined will be 3-element array because there are 3 elements here. So we make a temporary array and our I is 0 and now our j is 1 and our k is 0. So we compare I and j index 5 and 90. Which one is smaller? 5 is smaller. So we copy 5 over, increment j. So now our j is 2 and we increment k. The next element that gets copied is at 1 kth index, which is 1 now. We compare 90 and 72. Which one is smaller? 72 is smaller. So we don't move I because we are not copying anything from the right side yet. But 72 is smaller. We copy 72. We increment k. Now k is 3, and our j we increment that 3, but then that's more than the length of array. So there's nothing left on the right side to copy over. So whatever remaining on the left side gets copied as is. Right? So now this is sorted as well. 5, 72, and 90 is sorted. So we come back to the original array where we had divided into 2 halves, and we said we'll first sort the left side, which we did, and then we sort the right side, we did, and the next step is to merge them together. So now we have 2 arrays of 3 element each length. So we create a final array which is of 6 elements. We create a temporary array of 6 elements. 1, 2, 3, 4, 5. Okay, and this is our I is 0, and our j is whatever half plus 1, right? So the 6, so length is 6, so 6 divided by 2 was 3, and then so this becomes 3, right? So now what we do is, now k is 0 in temporary array. We compare ith and jth index elements. Is 0 less than 5? Yes, 0 is less than 5. So we copy 0 here. We increment k. So our k is 1. As we copied from the left side this time, we increment I. So our I is 1, j still remains 3 because we didn't copy anything from that end. Is 14 less than 5? No, 5 is less than 14. So we copy 5 over here. We increment k. Our k is 2. And as we copied from the right side, we are going to increment j. So now our j is 4. And I remains as is because we didn't copy anything. So now we compare, is 14 less than 72? Yes, 14 is less than 72. So we copy 14 over. Now our k is 3, our I is 2, and j remains as is because we didn't copy anything over. Now we compare, is 37 less than 72? Yes, 37 is less than 72. So we copy 37 over, and now our I becomes 3, which is greater than half of length, right? So we have crossed the border. So now we know that there's nothing left on the right side to copy. We copy 37 over, incremented I, and we increment k to 4. So now when there's nothing here to copy, compare with, because we have looked at everything, whatever remains in the right side array, we can just copy it as is. So we are at j equal to 4, starting from there to the end of array. We just copy things as is. Why are we not comparing it? Because we have exhausted everything on one side, and whatever remains on the other side, they are already sorted. So we can safely copy them over, and we realize that we have the resultant temporary array is a sorted array, right? Now what remains is our original array was that the result that we have, sorted result, is in a temporary array. So somehow we need to copy all this content into the original array, and we have a sorted array, right? Any questions? No questions. So let's quickly write a program for this, and if we have understood this well, we'll see how easy it is to write a program. And why is it easy to write a program is because we observed one thing. is we do repeated things here. First is we partition the array, and then sort each half, and then combine the result. That's what we're doing. We whatever array we have, we break it down. We sort the left hand side first, sort the right hand side first, and then we combine the result. Right. So it's a indication that it is something that we can solve using recursion because we're repeating the same process over and over again. So recursion typically is a good candidate for that. So now I'm going to share my screen, and we all can write a code together. Um, Let me know if you're having trouble seeing the screen here. And this is where we were last time. We looked at these different sorting algorithms. Today we are going to what we looked at is called merge sort. Is because we merge the sorted arrays into a final array, and let's do that. Let's write a program. So for this, let's make a Java class and let's call it merge sort. Let me know this is good enough of a font size. We just created a class called merge sort. I created it under the ARR package that I have. It's recommended to put it there so that all array related programs are together. Now, before we start writing, we should take a moment and talk about why is this a better approach of sorting than what we have seen already. What makes it better? So what makes it better is if we do the math of finding what the complexity of this algorithm is, we'll see that this algorithm is is n log n complex, and this log is to the base 2. So we can, right? So we see that it is n times log n complex. Now log of a number is it's generally a smaller number. Whatever we had looked before, they had a complexity of n square, right? So what n square means is n square is essentially n times n. So this is in the past that we have seen. So how does this algorithm help here is we have same n multiplier, that part remains, but in the previous ones we had a multiplication factor of n, but in this case we have a multiplication factor of log n, which is a smaller number. So this algorithm is going to take less time than the previous ones that we had looked at. We can quickly run an experiment once we have the code, and then we can verify it. But that's what you'll see is this program runs way faster, in fact, blazing faster than the previous ones. And with n, the n square is a much bigger number, but with bigger n, log n is not that high. So the product n into log n doesn't change significant if our n becomes bigger. Yeah? So it scales. This is a scalable solution. Whereas the whatever we have seen so far, they are not scalable. If we are sorting like 10 million records, then it's going to take 10 million times 10 million, 10 million. So it's going to be 10 to 12 time. And if you run a program, generate an array, it's an interesting thing. You should do it as a Java student, computer science student here, is write a, we already wrote code last time. Just take that and generate a 100,000 long random array and sort it, and you'll see how much time it takes. It will take like over minutes to sort, whereas when you sort the same array using this method, it'll take hardly a second. So it's a good experiment to try. What is drawback of this approach? The drawback is we always create a temporary array, right? So let's say our array is 6 element wide. We end up creating an array of 6 elements, which is temporary. We delete it later on. Now, if our array was 1 million elements, then we would have had created an empty array of 1 million length. So it is very expensive in terms of memory. We literally need twice the memory to sort, whereas all the previous methods that we looked at, they were in place, which means we were not making their copies of things. We were just using the same array and we were sorting it inside of it. So they were in place, and this approach is memory intensive. But that memory problem, it's not a big problem because memory is cheaper these days compared to how much time it saves. Okay, enough of that. Let's write a program real quick and build our intuition of understanding why are we writing the way we are writing. So first thing is we write a public method, and this is going to be public static void, and we'll call it sort. And what parameter will it take? It will take a comparable array. Um, so any element that implements comparable is a parameter it takes. Now, why do we use comparable? Because we are saying no matter what object you are passing us, we know that this object is going to implement compared to method, and that's what we need. We don't care if it is a name object, if it is an animal object, a school object, or could be anything. We are fine till the time it implements comparable. Oh.
Did you say something?
No.
Okay.
Read your message. Sorry.
Yeah, my laptop crashed, so I'm sorry about that.
Yeah, no problem. Yeah. All right. So, okay. So we'll write a method. So anyone who wants to sort will call this method. Now, what we talked about is we do certain things in a repeated way, which is we take the array, we partition it into halves, and then we sort the left half, we sort the right half, and then we combine it, correct? So let's just, whatever we think, let's just write it and see where it takes us. So we will create a private static method which does the real sorting, and we'll understand why. But let's start with it. This also takes comparable, and it says whatever data, and we're going to get a okay, fine. That's not an issue. We'll resolve this real soon. So first thing we do is we partition, right? So we say what is a midpoint of our array is data dot length divided by 2 is this is where we are going to break the array into half. And what do we do when we break array into half? We first sort the left side and then we sort the right side. So we call itself and we say now instead of sorting the whole array, sort only the from 0 to wherever the mid is, right? And then we say sort the data from wherever the mid plus 1 to the length of array. So data dot length. Now there's few problems here. So we are on this page, right? So we first divide the array into half. We sort the left half. We sort the right half. But now we are it's saying, oh, I can't find the signature, which means what we have identified is to find out if it is left or right half. we depend on these indexes. So left half will start at a 0 index and it will end in the mid. So if you look at the whiteboard, the left half is this. What is the length of this subarray is from 0 to whatever the midpoint is. And what is the length of where does the second subarray start? Is whatever the midpoint is plus 1 is where it starts and till the end, right? So it is, so that's why we add two more parameters here. We'll say give me the low index. So we'll call this as low index in the left array, and that becomes low index in the right array. So we say give me low index and give me high index. So that's what we say. So here, then what will our mid become? So our mid becomes not data length by half. It becomes whatever is the high index. As an example, when we're looking at this one, our low is 3 and high is 5. So what is a mid? Mid is high minus low plus low. So 5 minus 3 is 2 plus the low index is 3, that makes it 5, and that divided by 2. In fact, what we do is we take the high, 5 minus low is 3, that's 2, divide that into half, which gives us 1. 1 plus the low index is where the mid is, right? So what we do is high minus low, that is divided by 2 and then add the low to it. So this gives us where our midpoint in the array is, right? But okay, so we have taken care of sorting. This is going to sort the left half, and this is going to sort the right half. What we do after sorting the right and left halves, we come back and we merge them together, right? So let's do the merge. So we'll write a method merge, and what does it merge? It merges the two halves, which means it's saying take data, and my first half is from low to midpoint, and then where's the end of this is at high. Put all that into one. Okay? Before you do that, sort will not always start at 0, it will start at low. And then the high will be just where the high is. Okay. So now we need to write the merge method. So let's quickly write that. Rabbit static void merge. And what does it take? It takes a comparable called data and merge what? So starting at low to the mid, and then all the way to high. Merge all that. Now the question is, merge all that into what? So merge all that into a temporary array, right, at the very bottom. But where is the temporary array? We did not provide it. We have provided the merge mechanism, the actual data array, not the temporary array. So let's pass, as we need temporary array to combine the data, we need to pass that. This method will require a temporary array. What should be the type of the temporary array? It should be type of same type as the data, because it's going to hold the same type of value. We'll call it an auxiliary array. AUX. Now, as this merge requires an auxiliary array as parameter, we're getting a red line here saying you have one parameter missing, which means aux is missing. So what we do is, okay, we say fine, we'll pass the auxiliary array. Now where will this method get auxiliary array? We're going to get an error saying cannot resolve simple aux. So it is going to get it as a parameter. Let's whomsoever calls this, let them provide us what the auxiliary array is. So they are that in the parameter. Right? Here we're getting, okay, error here. So we just pass aux, going to pass aux here again. So whenever whomsoever calls this sort method is going to provide a temporary array, and that temporary array is forwarded to the merge. This is where we're going to use it. And here this is where the meat of algorithm is. So we are saying we're sorting left, sorting right, and now we are merging it together. So before we merge, remember we did this comparison when we were merging, and at the end we copied everything from temporary array into the final array is what we talked about. But to make it easy and skip that one step in the end, what we will first do is copy that original array into a temporary array, and then when we merge it into the main array, and then we have a sorted result without, we'll not need to copy it at the end. So when the sort ends, we have a sorted array already. So for that purpose, we'll say int k is equal to, starting at low index, k. How far should it go? It should not go more than high index, and then how should it increment? One index at a time, and then we just copy content from the data array into auxiliary array. So we'll say aux k equal to data k. So it's just a copy from one index to another. Nothing fancy happening. Now, remember we had this index I and j. So let's write that index I. And what is I? I is the low index. What is j? J is the high index, or in fact, j starts at the first index of the right half. So where is first index? It is wherever the mid is, plus 1 is the first index. So we have mid as a parameter. So we'll take our j is mid plus 1. That's where we start. And then what do? We had this k. Remember, we had this k, which was telling us where in this auxiliary array are we, where should the next element get copied into auxiliary array. So we'll have index k for that. So we'll say for int k, where should k start at? K should start at the low index, and it should not go beyond the high index. And then how should it increment? One index at a time. We compare one element at a time. Say if I is greater than mid, which means we have increment. Let's make that like a last. Well, hmm. Okay. Okay, we'll get to that. So when we were comparing two things, whichever was smaller, we would copy it in the auxiliary array. So let's do that. Let's see which one is smaller. If less, now we had made this. Well, we did not make it. Let's. So we need to. We actually did that, but in a different file. Elements. We have this method called compare, right, and exchange. So so let me copy that and put that in the array utils so that we can use it in all our comparisons. Right. So instead of compare, let's call it less. And instead of boolean, let's let this return a boolean, because we just care about is left hand side element smaller than right hand side element. We don't want to know how small it is, so we just need a boolean. We're saying compare those two elements, and if this is greater than if it is less than 0, then return a true, right? So we are saying if left hand side is, when compared with the right hand side, it returns a negative number. It means left hand side is smaller than the right hand side. So return true when it is smaller. So now we have that method to compare, and we'll use it here. So we'll
I was
say,
absent last week. So what do I do here? Should I just wait?
come again?
I was absent last week, so I don't have that method.
We don't have a method. So quickly write it down. It's just 2 lines.
Oh, I thought there was something else from like before that we had to know.
Yes, we did talk about what comparable is. Where did this come from? So while you copy this, let me know once you have written this, and I'll explain it just to refresh everyone's memory, and then we'll get introduced to this as well.
I got it.
Writing this?
Yeah.
Okay. So last time we realized is when we have an integer type array, I think you were there when we talked about these int arrays and stuff. The problem with that is every time we do any operation, if an array is of different data type, then we have to rewrite the whole thing again just for that data type. So Java provides a mechanism which says any class that implements interface called comparable. So as an example, what we did was we had this phone number class, and we added a comparable here, and this is how you uh, write a class which uses an interface, Java interface. You say your class is implementing an interface. So the moment you do that, you will have to write a method compare to, and this is a signature of compare to. And this method will let you compare two objects of same type. So if you have two phone numbers, and you can say phone number one dot compare to, and pass the second phone number as a parameter. And then here you find out how those phone numbers should be compared. So using this interface comparable tells Java that no matter what object it is, let it be a phone number, let it be a teacher or whatever it is, doesn't matter. If they are implementing comparable, they must have um, this method compared to. So that's a guarantee that implementing that interface does. It guarantees that you will have that method. So that's why we are saying now is give us an array of any type of object, but they should all be of type comparable. So they all must be implementing comparable interface. So we can sort any object now. It doesn't have to be different methods for each type, right? So as a comparable has this method called compare to, we are saying compare left hand side with right hand side. If the result is equal to 0, it means they both are same. If result is greater than 0, it means left hand side is bigger than right hand side. If the result is less than 0, it means left hand side is smaller than right hand side. So we are saying when we compare it, if the result is less than 0, it means left hand side is smaller. And then as this is Boolean, that's what we need. We just need to know if left hand side is smaller or not. And this is going to exactly tell us that. Here we use that. We say.
Wait, sorry, go back.
Yes.
Okay, I'm done.
Okay, perfect. So we come back to our merge thing here. We say, let's compare. Why is it not showing up here? Is because that's private. Okay, let's make it public. Make that public. And then when we come back to our merge, we say compare. What do we compare? We compare whatever is at ith element with whatever is at j index, right? So how do we do that? We say compare. So what we're doing is we are comparing right hand with the left hand thing. So we're going to say compare auxiliary array j with auxiliary array element I, and if that is less, then what do? Then we, so what it is saying is compare j and I. If j is less than I, then copy j first. Right? So let's say in here, j was I was 0 and j was 1. We're saying compare j with I. Is 0 less than 14? Yes, it is less than 14. So what do is we copy whatever is at I into auxiliary array k0, and then we increment the I because we have copied from the right hand side. Right? That's what we're going to do. Is if it is less, then first thing we do is we copy at what index? At kth index. What do we copy? We copy whatever is in auxiliary array j. And then as we have copied it, what do? We increment j. So we can just say j plus plus. Okay. What this is going to do is it is going to copy whatever is in the auxiliary array at jth index into k first, and then it is going to increment j. Right? But if that's not the case, then what do we do? Else, so if okay, now there's a problem with this approach, right? The problem is, let's say in the next iteration, we compare j with I, 37 with 14. Now, is 14 smaller than 37? Well, is 37 smaller than 14? No. So what do? We copy I instead, right? So we copy 14 over, and our k was 1, so we copy 14 over the 1th index, and we increment I. So our I becomes 1, but then the moment it becomes 1, it is outside of the subarray. So we need to find a condition. So there's no point in going forward because we have already exhausted the array. So before we do anything, we should check for that condition. Is if I has gone beyond the midpoint, then what do? If I has gone beyond the midpoint, then whatever is remaining in the j, we just copy it over as is, right? So we're saying if that happens, then at kth value, whatever is in j, we just copy it over. We say auxiliary j plus plus, and then increment j. Keep incrementing it till we run out of j. So if we keep doing that, eventually we'll run out of all the j's, which means we'll reach the end of the right half. So we'll put a condition for that as well. If j has gone beyond the high, means now we have. So how do we know we have exhausted the left half? Is when I goes beyond the mid. How do we know we have exhausted the right half? Is when j goes beyond the high value. If that's the case, what do we do? Whatever is in the I, we keep copying. Right? So data a is equal to auxiliary I plus plus. Then we do that comparison. Now, if j is smaller than I, then we copy j over. Now, if j is not smaller than I, then the only thing remains is either I and j must be equal, or I must be smaller, right? So in that case, we say else instead of else data at k is equal to auxiliary I plus plus. And this is it. This is the program, just a merge sort. We have just written it. There's one thing pending. Is whenever we write a recursive method, the first thing we should try to do is to find out the break condition. When should this method stop? This method will stop only when and low is greater than or equal to high. When that happen? That will happen when you are left with just one element array. There, the low is also same index, high is also same index. In that case, you have one element array, and you can't break it down further. So you just say this is already sorted, and this is it. This is industry grade what sort program. Let's quickly test it out. We have this mechanism. We say run. So we'll implement a run here as well. We say public static void. We need to generate an array. We generate an array of integer type, and we already have this method to generate array with random elements. We just use that method to get a comparable is an object. It expects an object, right, of type comparable. But this method here returns an integer type, a primitive integer type array, which doesn't have an integer is not comparable, but the object integer is comparable. So we write a method that will say public static, and this returns a integer array, an array with random elements. And this is a little inefficient way of doing it, but just for sake of experiment, in the name of science, it is fine. We'll say element int low, int high. So int low and high are the range between which you want to generate a number, and we know that we have a method which generates an integer type array. So we'll say int auxiliary array is, we call the existing method. We pass all the parameters to it. We do that, and then we create an integer array data is equal to new. How big should this be? It should be as big as the length of auxiliary array. So we create an array, and then we just copy the content over. For int I equal to 0, I less than auxiliary array dot length I plus plus. This has nothing to do with sorting. They're just creating a random array. So we'll say data I is equal to I. Now why does it work is because an integer object is like Java does auto boxing, so it will automatically convert a primitive int into a into object. So this will just work fine. You don't need to do a typecasting here. Once this loop is over, we return the data. This is how we'll create a array with random elements. I think I misspelled this. This is random. Okay, so now we have this. Okay, so here it is. It is complaining about the both methods have same signature. So Java will get confused which method to call. So we need to change the name on it because we don't want to change the parameter. So we'll say random integers. Okay, the ambiguity is gone now. So we come to merge sort, and in our run method, first thing we will do is we'll create a random array. We'll say integer data is equal to array utils dot generate. How many elements do we want in it? Let's say for sake of simplicity, we'll have 20 elements, and in what range? Between, let's say, minus 100 to 100. Let's have some negative numbers to make sure things are working for us. One thing we did not So we did write industry grade code to sort, but then there's no way to call this method because it's private. We had created this public method, but this is empty. So now we'll call,
Can you go back down, please?
yes. So right here, we're just creating a random data array.
Okay, I'm done.
Okay, so we come back here, and this is a public method, and this is not doing anything right now, and we'll change it to call the call our sort method, which implements the code. So how do we do that? The moment you say sort parameter, okay, we have data. We don't have auxiliary array, right? So that's a required parameter. So we'll first create an auxiliary array of what type? Of some variable type. We'll say this is my auxiliary array. How long this array should be? It should be as long as the data is. We'll say data.length, create a temporary array, and then we pass that. Now what else it is asking for? It is saying where is your array starting at and where does it end? So as we are passing the whole array, this is the entry point, it starts at 0, and where does it end? It ends at data.length minus 1. Because array indexes are 0 based, so the last element will be at index data length minus 1. So now our code is ready to run. Now before we sort it, let's print out the contents of it. So we'll say system.out. So were you all able to write this down?
I'm getting some errors.
What error are you getting?
It's in the merge thing under I and J. It says variable I is already defined in the scope and variable J is already defined in the scope. Like where it says int I equals low.
Yeah, it's saying, can you share your screen? Maybe you have written those somewhere outside of the brackets.
Okay.
Share your screen real quick.
I'll share.
Um,
Okay, I just shared.
Perfect. Let me take a look. Okay. You have written int j again inside the for loop.
In
So
here.
remove that.
Which one
Yeah.
should I keep?
So remove the int word from before j on line 36. Yeah. So int j has already been declared above. So you just need to use it. Right?
Okay.
Can you see the problem in your head? What is the next option? Why is it underlining the if?
Wait,
I
hold
will
on.
define. You have I
There we go.
on top.
Compare it in again.
Yeah. There's error again. What is it complaining about now? Go hover
So
over
is it better now?
Yeah, you can actually delete the line 32 altogether because you have already done that on line 21.
Okay.
Yeah. So, and why is it underlining under if? Hover your
Under
mouse
here?
over line 38, yes. And collapse.
It's not an error. It's just like a, I don't know.
Yeah, it's like a suggestion. Right?
Yeah.
Yeah, that's fine. Okay, perfect. Anyone having any questions so far? Okay. Yeah, stop me if you have and then we can go that. Okay, coming back to the program. So now we're going to print out contents of array before sorting. We'll say before sorting, And how do we print that? We'll say we have this utility method array dot print array contents. Then we pass data to it. So, Paraksha, you were not present last time. Uh, write this piece of code in your array utils class.
Okay. Which one? The print array contents?
Yes.
Okay.
And then, yes, you might. You were there last time. No, you weren't there. Right? So you may want to write that as well.
Wait, my print array context looks different than yours. Like mine, like it doesn't have the T before it, and it's a little different in the code, but it's pretty similar. Should I just change mine to?
Yeah, so keep that as well, and then.
Oh wait, yeah, I just realized I have the top one, but I don't have the bottom one.
Yeah, so write the bottom one.
Okay.
So what the bottom one does is, see on the top, it takes integer type array as a parameter and nothing else. So if your array was a object, then the above method won't work. That's why we wrote this another method which says, no matter what object it is, I'm going to print the content of it. And here instead of slashing, put /t.
I finished typing this. Can I see the other one?
What other one?
I mean the code for the merge sort, like the one that the print code.
Okay, give me one moment. We'll get there. So everyone has this in their code now?
Wait, sorry, I'm still copying.
Okay.
Okay, I'm done.
Perfect. So let's go back to merge sort, and so we'll say we'll print the array contents before sorting, and then let's sort it. So we'll say sort the data, and we'll print out the content after sorting. So I'm just going to copy these two lines and paste it here, and I'll change before to after. Once you are done writing this, then go back to hello string where our main method is, and we can comment all this out if you want it. And we can say merge sort of my algorithm.
Oh, wait, sorry, can you go back to the merge sort thing really quick? I didn't get like the last print statement. Okay, it's just after sorting. Okay, I'm done.
Nice. So we go to our main and we just say merge sort of run, and then we run the program. Oh, there it is. Null pointer exception. Wow. Okay. So it is saying that somewhere we are passing null value to this, and it crashes right here. So where is it being called from? It's being called from this location, which means uh, uh, what are we missing? What are we missing is the merge. Less Sometimes it can get tricky. So what is happening here is one of these is null. When would that happen? When would which means high. That's there. Which means somewhere we are missing here. Yeah, so this is simple copy. So it must be somewhere before this, which is right here. What's going on? Head. Now we'll have to debug this. So after all, this is not industry grade then. I think there is some mistake somewhere. Let's quickly debug that. For this, let's make a smaller array so that we can debug. Debugging 20 elements is just too much. Let's see if this works. So, okay, we are getting an exception. We'll put a breakpoint and then we'll do a debug. Okay, so it's hitting here. You know what? It'll take some time. Let's not spend that time debugging. I'll try to find what the problem is, and we'll share, what it is next time. And meanwhile, if you guys feel free and run this program at home and see where it is failing, and you could do exchange of notes next time in the next session. But this is a general. Wait a minute. Could the problem be here? Okay, no. So, okay. To debug this at home, there is something off tying with somewhere. So the content of the array is null, and then you're passing that as a parameter, and then the compare fails because we are passing null to it. We need to find out what happened. Okay, that's exercise. Figure that at home, and I'll find out what's going on and tell you next time. We have a few more minutes. If there are any questions, I can answer them now. Else, I wanted to talk about another program. You know what? We have 10 minutes. Too less of a time to talk about it. But this program of merge sort is actually used by Java libraries. So another way of sorting, which is easier way, is to use what Java already provides you. And you can do that by calling array class array sort. That's it. We pass data, and then this does the sorting. But in this case, we are using sorting mechanism implemented by Java library. So let's comment out this line here for a moment, and let's just paste that. And this is a quick way to sort it. You don't have to worry about how sorting has been implemented. This will just work fine. And let's quickly see that. Yeah, there it is. It just worked fine. Now, internally, what Java sort does is actually it does a merge sort. Well, not entirely true. So Java uses two sorting mechanisms. One is merge sort, and another one is called quick sort. And quicksort is one of the most popular algorithms in computer industry of 20th century. So why does Java implement two sorting mechanisms, and how does it decide which one to use when? It's very simple. Um, um, so let's say when these are numbers, right? Um, and if
Wait,
you
I have one question.
yes,
Wait, so what did you change? You made it arrays dot sort? Is that
so
it?
no, so I couldn't make our program work. So that's like an exercise. You guys figure out at home what's going on by putting a breakpoint and oh, I think I know what's going on. Okay, this should have been else if that was a problem. Okay, so put that else if we'll come back to arrays. Got our own program working now. On this, voila, there it is. Our
Uh,
program works.
I don't know, but mine still doesn't work after that.
It doesn't work. Okay. You want to share the screen?
Yeah, it has a problem in line 14 for me, which is the sort data aux low and mid.
So it's
So like
giving
sorting
you
the left half, sorting the left half.
what's the problem there?
It says I don't know, it doesn't really say anything. I'll just share my screen.
Yeah, share the screen. All right. So scroll up on the error in the output screen.
Yeah, they're all at that same line.
Yeah. Okay,
It's
go
like
all the way to the top. There it is. So it's a Stack Overflow problem, right? Which means your break condition is not working. So in your sort, see there is you have int mid go up. Yeah, you have integer mid. So you're not checking when should this stop. So it will keep calling itself forever. That's what is happening. So you don't have a check to end the calls.
okay.
Just keep calling. So the fix is real simple. If you look at my screen, um, you'll see this line number 13 with checks for that. So when should we stop calling itself is when you reach to one element array. And that will happen when your low and high index is exactly the same. So it's pointing to same index. That's one element. What do you do? Like how do you sort that element? You don't sort it. You just it's already sorted. So you don't call itself, you just return. So that's a break condition in your recursive method should always have a break condition. And the break
Wait,
condition,
I don't really get that condition though. How does that? I don't get what it's supposed to do.
so what it is saying is, um, so okay, what do we do? We first break the array into half, right?
Yeah.
Which
Hmm.
is at line 14. And then we sort the left half, we sort the right half, and then we merge, correct?
Hmm.
Now, let's say we have 6 elements. The first time, we'll divide it into half, 3 and 3 each, right? And then
Yeah.
we call the method and we pass 3 elements to it when we do the sort left half. Now, so it will call itself, and now it will break this array into two halves,
Hmm.
one element and two element array, right? Now it will
Yeah.
try to it will call itself and pass 14, which is single element, and say sort this for me. Now, what is the mid of this? Your I is your low is 0, your high is 0. What is mid? Mid is also 0. So what you'll do is you'll call itself again, and you'll keep calling it um, and passing that one element. So when you reach to this one element, you really can't sort it. It is already sorted. So you say, in case when your I and j are the same, it means it's already sorted. Go back to the next level, like the previous level.
Uh, I think
So
I get it.
okay. Now,
Okay.
now let's look at a case here. When we have 6 element array and we divide it into two halves, right? So we say go and sort the left half, come back here, go and sort the right half and come back here, right?
Uh-huh.
So at this level, go to the next level, sort it, come back to the same level. Now when you're back to the same level, go to the right, sort it and come back to the same level. And now let's merge whatever we got at this level. Now, when the first level is break into half, go to the left side. Now, here we say break this into halves and then sort each one and come back. So we break it here. Now there's 14, one element left in the array. We say go sort this and come back. But this is already sorted. So we don't need to further break this down, right?
Yeah, I think I get it. Yeah.
This is our end condition. We stop calling ourselves because we reached one element, so we can't sort it anymore. So this is already sorted. So we go back to the next level, which is now go and sort those two. And when we have sorted those two, then we combine it.
Okay.
Right? So this is our break condition. When should we stop calling ourselves? Is when we reach to one element. Right? So I hope this is working for all of you.
Mine still have errors. It's in different lines now.
Where do you get error at? Do you want to share a screen?
Yeah, for some reason it's in the same spot. I think I'm still sharing.
Okay, give me one moment. Okay.
It's in two different lines actually.
Scroll all the way up. Oh, because you're calling sort and passing 0 and width. So instead of 0 and width, pass low. Instead of 0, pass low. And for the other sort, instead of data dot length minus 1, pass high. Yeah, and then close the package. Save it and run it.
Yeah, it works.
Nice. So as fun experiment, you all can have like an array and sort it using three methods that we have seen and find out how much time each method takes. It'll be a very interesting experiment.
Mm-hmm.
So coming back to here is, now we know our method works. So we'll see what Java offers. Java does offer a sorting mechanism. It's array.sort, and it also does the same thing. It will just sort things for you. So you don't have to write your sort mechanism every time. Now, as I was saying, Java implements sorting in two ways. One is using merge sort, which is exactly the same thing we have seen here. Java uses that. Java also uses something called as quick sort, which we'll see in the next session. And even that is a very genius idea. And we'll see how a simple idea can improve solutions. But how does Java know what to use when? Now, when we call array.sort, we don't tell it which algorithm to use. Java picks it up for us. So how does Java know which among the two, merge sort or quick sort, should it pick? So it looks at what are you passing? Are you passing an array object? Are you passing an object array or are you passing a primitive array? Which means in this case it is integer. But if we had, let's say, int, um, in, let's say 10 elements, that's an example. If we had an array of this type and you call array.sort, then Java will see that this is a primitive data type. So it will call something called as quicksort. Because why would it do that? From our previous two sessions, if you recall, in the last session we talked about stable versus non-stable sorting. So what stable sorting does is it doesn't move things in an array too far apart. So if two elements were together, then they'll retain their order. Uh, Whereas unstable or non-stable sorts are, it will sort the output, but then it may rearrange things a lot. So in this case, merge sort is a stable sort. Why is it stable sort? Is because it preserves the order. It sorts everything, but if two elements were together, then it would have preserved the order in which they were existed. That's why it's stable. And there's a rule of thumb to find whether an algorithm is stable or not, is to look at how far away the comparisons are. So in this, we see comparisons are typically just one element at a time, right? So that's why it is stable, because it's comparing its neighbor. Uh, the cases when comparisons are like far apart, then there's a chance that things will get mixed up. So as this is a stable search, when you pass Java array dot sort method an object array, Java has no way to know what is in the object. So it will use merge sort so that when the output is returned, it returns a stable output. It doesn't rearrange things for you. But if this is a primitive integer, let's say it had 0 followed by another 0. Now in the final sort, how does it matter which 0 comes first or last? It doesn't matter. It's just a primitive type, right? So in the sorted result, you would have seen two zeros, 5, 14, 37, and then 72. How would you know? So let's say this is 0 number 1 and 0 number 2. How does it matter if after the sort we got the second 0 first and then the first 0, right? It doesn't matter. We don't, in primitive type, we don't preserve, there's no attribute associated with it which we need to preserve. That's why Java will use quicksort, because ordering is not important. But when ordering becomes important, then let's say if you have list of students and then you sort them by first name, so everyone whose name starts with A will come first, and so on and so forth. And now you want to sort them based on their last name as well. So you will use a stable algorithm to sort such cases. Else now you will have people sorted by their last name, but then now their first names might be messed up. So you want to preserve the first name sorting. So maybe next session we'll kind of do that real quick and find it out. So I think that is it. This brings us to the end of today's session. Let me know if you have any question. Else you all can drop off, practice at home these algorithms, and yeah, run experiments. Have fun with it.
Thank you.
Thank you. Have a good
Thank
night.
you.
Thank you. Bye bye.